Hello and welcome. Today we're going to take a look at these 70 volt line transformers that are commonly used in public address type systems and music distributed through offices and so on and so forth, and using them as matching transformers for older tube equipment. A lot of early ham radio equipment and early shortwave receivers didn't have an audio output transformer in the receiver, and most commonly they were built into the external speaker, and a lot of these radios had a 500 ohm or 1000 ohm impedance or both output, and you needed a matching transformer if you wanted to use an 8 ohm speaker. This was very common back in the tube days on ham radio type equipment. And there's been some videos lately about using these for matching transformers, and they can be successfully used. However, some mistakes have been made, and we're going to try to clear some of that up today. And I understand how these mistakes were made. It's very easy to take something like this little Chinesium impedance meter here, and because it's digital, we take it at face value. But these will not give you the correct results to measure impedance on these transformers. They give an impedance reading which is basically meaningless in most cases, because you don't know what the test frequency is, and impedance is based on frequency, reactance versus frequency for impedance. Something like this audio impedance meter in the background here is designed specifically for measuring impedance on audio type equipment, speakers, audio transformers, and so on. Surprisingly, this little Chinese unit will give you accurate readings on speakers, but on transformers themselves, they will give you false readings, very false readings. The second mistake that's often made is people forget to terminate the output of the transformer. The name transformer, it transforms impedance. So if you have a transformer with an 8 ohm output, a known 8 ohm output, you need to put an 8 ohm load on the output to measure the impedance on the primary correctly. Otherwise you'll get an incorrect reading. We'll demonstrate that here in just a moment. The fact that this meter will give you no difference in impedance on the primary, whether or not the secondary has a load on it, is a warning in and of itself that something is wrong, because the transformer should reflect in the primary any change in impedance or resistance in the secondary. If you're not getting that reflection back through the transformer, you're not getting a true impedance reading. This meter in the background tests at 1 kilohertz, which seems to be the standard test frequency for most audio test equipment. This doesn't use any frequency that I can figure out, and we'll show you on the scope that it's just a series of random digital pulses of varying lengths, where this is a uniform square wave output at 1 kilohertz. And let's hook up a couple things in here real quick and show you what the results are. And actually, before we even do that, before we use any of the test equipment, let's take a look at some simple math. And when I say simple math, it has to be very simple for me to be doing it. Extremely simple for me to be doing it. I am not a mathematician. However, even I can follow this, and this is directly from one of the manufacturer's websites. When looking at these transformers or using these transformers, there's a way you can actually calculate what the primary impedance is. And some very simple math using variations of Ohm's law here. Watts equals voltage times current, or current equals voltage divided by resistance. Therefore, watts equals E squared over R, or divided by R. Now these are 70 volt transformers. Therefore, A 70 volt system, which is actually 70.7 volts squared, or 70.7 times 70.7 is 5,000. So the wattage equals 5,000 divided by the impedance, or R 5,000ths divided by watts. Resistance equals 5,000ths divided by the watts. Now these transformers are in watts: 10, 5, 2.5, 1, 0.5, and a quarter watt. So the 5,000 divided by the 10 watts is 500 ohms. That means the first winding, the 10 watt winding, the black and the brown, should result in a 500 ohm impedance, and that would be the pair you would easy for me to say, you would want to use to match a 500 ohm output on one of those receivers. 5,000 divided by the 5 watt, it would be 1,000 ohms. So if you had a 1,000 ohm output you wanted to match, you would use the black and the red. Let's say you wanted to match 2,000. 5,000, and that's the 2.5 watt setting. 5,000 divided by 2.5 is a 2,000 ohm impedance. Told you this was going to be simple. This is really simple math. 70.7 squared. 70.7 squared is 5,000. So 5,000 divided by the wattage gives you the impedance. And so you actually don't even need to use an impedance meter on these. This is directly from the manufacturer's website, and there's several of them out there. If you just look up line transformers, this formula is on many of these sites. It makes it a lot easier. However, let's prove it. Okay, I've hooked up one of these little Chinese LCR meters to what I believe should be the 500 ohm primary, the black and the brown, and I have left the secondary open for the moment. This should give me an incorrect reading on the primary. What's interesting is if you go through the different windings with this tester, you'll get various impedance readings. You'll get various inductance readings, which is probably correct. The inductance reading is probably correct. It's the impedance that's wrong because it's not testing at 1 kilohertz. And actually some of the windings, this will report them as being an FET, a field effect transistor, which we obviously know is wrong. So you know right away something's not working correctly. But let's see what it says on what should be the 500 ohm winding. It's testing, and it's returning 41.9 ohms. That's a long ways from 500, and an inductance of 2.82 millihenries, which is probably pretty close. Now, if this is working at all, when I put an 8 ohm resistor, there's an 8 ohm resistor here, this would be 16 ohms, this would be 4 ohms in combination. So I'm going to hook up on the secondary an 8 ohm load, and this transformer has an 8 ohm secondary for the output. And we should see a big difference in the primary impedance if this is working correctly. And here we go, testing again with our load. 42 ohms. It did not return an inductance reading. Now it's simply returning a resistance of 42 ohms. It was 41 before without the output load. Not a very big difference. Something is wrong. So let's try the real tester. Okay, now we have the audio impedance tester connected to the same brown and black leads, which according to the calculation should be the 500 ohm impedance. And I've left the 8 ohm resistance on the secondary connected, so we should see something very close or in the region of 500 ohms. Let's turn on the test. And what's wrong here? Something's not working. What did I do wrong? Okay, so you've got to be smarter than the equipment you're working on. Too busy talking, not paying attention. I had it on the 200 ohm max scale, and that's why we weren't getting any reading. So I'm now on the 2K max scale, and we have a reading of 527 ohms, which is pretty darn close to the calculated 500 ohm impedance that the math said the 10 watt winding should have. Let me disconnect the output now. I'm going to remove the 8 ohm load, and we've gone into overload. That primary impedance is now 2.62 kiloohms because it's reflecting the infinite impedance on the secondary because there's no connection. And if I hook up the 8 ohm load once again, we're back down to roughly 520 ohms. Let's go down to the lower scale. So it's 527 ohms on that primary winding of the black and brown. That's the 10 watt winding. Following suit, the next winding in line would be the red wire, and according to the math that should be 1 kiloohm. So let's go there. 940 ohms, pretty darn close to a kiloohm, or 1000 ohms. The next winding in line should be 2000 ohms if everything is working. 1800, pretty darn close. So the math works. The differences are errors in the meter. This is only a 2% accuracy meter, and you know, there's going to be variations in the transformer. I'm actually using an 8.1 ohm resistor. Now I'm going to hook up a speaker that's close to 8 ohms. Not exactly. Actually, I think this measures 9 ohms, if I remember, but not to worry. It'll give us some indication. You can hear that 1 kilohertz tone in the background. And again, almost 2 kiloohms on that winding. If I go back to the red winding, we should see 1000 ohms because we're reflecting back correctly. And if I go to the 500 ohm, we should have the loudest signal we've heard yet. And there it is, a little bit louder. 545 ohms, pretty darn close to 500 ohms. And here's something of interest for those trying to match oddball impedances. Right now I have an 8 ohm load. The primary is 528. Let's say we had something other than 500 ohms, like 800 ohms. Well, if we put a 16 ohm speaker on there, which is a common speaker, we could change that to 800 ohms. It would reflect the impedance back into the primary at 800 ohms using a 16 ohm load, 2 8 ohm resistors in series to simulate the 16 ohm speaker. Likewise, we could use a 4 ohm speaker, which is the 2 8 ohm resistors in parallel, and we could reflect an impedance of roughly 300 ohms if we had to match to 300. And by mixing and matching the primary windings and changing the impedance of our speaker, we can come up with a whole plethora of different impedances. And you're not stuck necessarily using these two wires. You could take your impedance between the yellow and the red. There's no law that says you can't use the windings, you know, because some of these windings are higher impedance and you can divide them up any way you want and come up with different impedances. It will work. Now, what's the big difference, you might ask, between this and this? What's coming out of this? Well, let's put it up on the storage scope and see what comes out of the little Chinesium meter. I should have zoomed out a little bit first. And we'll see the difference in what's coming out of here versus that. Oh, before I do that, let's take a look at what it says. I'm connected to what is labeled as a 3.2 ohm speaker, is what it says on the frame of the speaker. The meter says 3.4, pretty darn close. I have what is labeled as a 16 ohm speaker. Now let's see what that one reads. 16.8 ohms, pretty close. I also have a 4 ohm and an 8 ohm speaker combination here, but I think you get the idea. It, you know, it pretty accurately reflects in the meter, but surprisingly, even this little Chinese unit, which won't work on the transformers. I promise you, you're going to get erroneous readings. However, if all you want to do is test the impedance of an unknown speaker, Let me get the little meter connected up to the 16 ohm speaker, and surprisingly, and I don't know why this works, but they do work on the speakers, or it does work on the speakers. It says 16 ohms, the speaker's labeled 16 ohms. Let's try the 3.2 ohm speaker. And this seems to work up through or down to, you know, between, I don't know, 30 ohms and 8 ohms, or 3 ohms rather, excuse me. Let's see what it says on the 3.2 ohm speaker. It says 3.1 ohms. I think that's close enough. So if you have an unknown speaker, a speaker of unknown impedance, you can use these to measure the speaker impedance. But they will not work on the transformer correctly, and we'll show you why in just a second. Because that little Chinese meter is designed to test transistors, diodes, capacitors, inductors, what have you, it sends out a whole string of pulses. There's a stepped pulse here, there's a negative going pulse, a couple of positive triggers, or from negative to 0, and then back up to 0 point, and then a positive pulse, and this train continues on and on and on. I have 100 milliseconds per division. Let's try it. Oops, let's knock the camera over, why don't we? Let's go to 500 milliseconds per division and see if we can capture some more of that. And see what we have. It's going to take a few seconds for it to write it to the screen. Oh, I just caught the tail end of it at that point. But as you can see, that's certainly no 1 kilohertz test tone. There's probably not enough memory in this scope to catch the whole sequence, to be honest. This is a rather old Tektronix 360. Oh, there we go. We got a lot of the sequence that time. You can see it's a whole series, positive going pulses, and it's merely not centered up on the 0 line. Put it right there. We've got a series of negative going pulses. They go negative, then 0, negative, 0, blah, blah, blah. Then we jump up, we have positive 0, positive 0, positive 0, and then it swings a couple of ways and back and forth. Who knows what they're testing, but they're swinging back and forth in polarity because they have to test for diode junctions in different directions, all kinds of stuff. But it's certainly not testing at anything near a 1 kilohertz tone. Hence, we don't have the ability to accurately test the impedance of an audio transformer. Why they even bother putting impedance on the display, I don't know, because it's not referenced to any frequency. Therefore, it's kind of meaningless. The inductance reading is correct, or as you know, it nearly matches my other equipment here as far as inductance goes, but as far as impedance, it's not testing at the correct frequency. And here we have the audio impedance tester, which is specifically designed for testing impedance in audio systems, and our 1 kilohertz square wave. Now these little spikes are, you know, kickback from the speaker, and there's going to be some noise in the signal. But from this, by using a known 1 kilohertz tone, the unit can actually derive what the audio impedance is going to be, or the impedance at audio frequencies will be for this transformer or this speaker or whatever you're testing. So that's why the little Chinese meter will fool you. It'll give you a reading, and we all tend to get stuck into that. It's a digital thing. It must be giving me the truth. And those of you who watch regularly will recognize that I've been bit by that bug before myself. When I was testing some piece of equipment using one of my digital voltmeters, and I was getting readings that didn't make a lot of sense. And it took me down the rabbit hole until I realized that I had to use my low impedance VOM, which I'm always telling people, use your VOM, and I forgot my own rule. Once I started using my VOM, of course, all the readings began to make sense. At any rate, hope this was helpful to somebody. Let me move the camera back down. Oh, and before I go away, if you're interested, places like Amazon have these meters for about $150. All this is used for is audio, and you probably don't do enough to justify buying one. Remember the formulas. If you're using one of these 70 volt transformers, the math is real simple. It's 5,000 divided by whatever the wattage number is on the primary. As long as you have an 8 ohm, or you're matching the impedance on the output. Some of these have 8 ohm and 4 ohm outputs. Some of these have 16 ohm outputs. If I went to a 16 ohm speaker, my 500 ohm impedance would go to 1,000. If I went to a 4 ohm speaker, that primary impedance would drop to 250. So just remember those simple formulas, and you can come up with what the impedance of these wires is, at least the ones that are marked. If you want to start mixing and matching, or if you have unknown audio transformers and you don't know what their impedance is, then you might want to pick up one of these meters. I picked it up because I had a box full of old audio transformers. I had no idea what their impedance was. Now I can actually measure them. Alrighty, one more quick test for the disbelievers out there, because I know somebody's going to say, oh, these these matching transformers are special cases, and they are not. I am going to turn this meter back on, and I am going to connect. This is an actual audio output transformer rated for 4 ohms with a 5K primary. So if I hook up to the primary side and get my test leads ready for the secondary side here. Remember, I have a 4 ohm, the light's bad here. You see the 2 resistors in parallel? That's 4 ohms, 8 ohms and 8 ohms. And I could go to an 8 ohm or a 16 ohm impedance. So we'll start out with the correct impedance for the transformer, which is 4 ohms. We'll connect the leads up. And if I'm not talking out my wazoo, this should show us about 5K ohms. 5,800. Pretty close. I am going to change this over to an 8 ohm resistor. And as you can see, we went from 500 to 10K. Or excuse me, from 5K to 10K, not from 500. From 5K to 10K, we've doubled it. If I go to 16 ohms, we're at 18K, almost 20,000 ohms. So you can pretty predictably come up with what the primary impedance will reflect by doubling or halving the impedance on the output. Here's another transformer. 8 ohm primary, or excuse me, 8 ohm secondary, 3K ohm primary. So we'll connect this up to the meter. No load on it. And it's off the scale. It's not even reading. So let's hook up our 8 ohm resistor. And see what we get. Whoops. Get on here. 3K ohms. 3.2K. So there you have it. Hope that helped some people. Hope it cleared up some mysteries. If you enjoyed this video or got something useful from it, please give me a thumbs up. And a subscription would be welcome. The more subscriptions I get, the more people on YouTube will find me. The more of these videos I'll be likely to make. And better the content should become, hopefully. I'm the Radio Mechanic. Thanks for stopping by. See you soon.